Hello friends, today we will learn about eccentric loaded connection, and this time we will see a bolt that is in shear as well as in tension. So we have a bolt that has tensile force as well as shear. If you remember, in the last video we discussed eccentric loaded connection, and that time we have a bolt that only contains shear forces. But now this time it is a combination of shear as well as tension. So let us try to illustrate this. So we have this structure, and this is the column we have in this case, and this is one beam and this is the second beam we have. Now if you see this beam and this column connection, so this the flange part of this column is connected to this beam through these bolts. So we have bolts here. Now let's say if some loads are coming on this beam from the top, so this load will try to rotate this part. So basically there are two actions due to this load. This load is trying to force these bolts in the downward direction, so there will be a shear force on these bolts in the downward direction. And another effect due to these forces are coming, that is the moment. So this force is eccentrically loaded, so this will try to apply a moment to these bolts, and these bolts will try to pull out, that is a tensile force will be generated inside these bolts. Similar for this beam, basically the only thing is in this case this beam is connected to bed of the column. So similarly here also these bolts are in direct shear, that is trying to push it down, and there is a force that will try to pull it in this direction. So there is a tensile force as well as shear force in these bolts. So we can illustrate. So let's say if I have a bolt, so this is the same bolt, let's say any one of the bolt, either this one. So if I draw this bolt here, there is a force that is acting in this direction. Of course other force will come in this direction to basically balance this. So there is a shear force that is coming, and there is a tensile force on this bolt that is coming. So two forces are coming, shear as well as tension. So in this figure basically this is the part that is coming from beam. So this is a plate coming from beam, that is this connected plates, this plate, and this part is coming from column. So this is the column flange. So we can call this as column flange, and this is bracket, that is the builded part from the beam. So this is beam, and we also call this as a bracket. So if you do the finite element analysis of this joint or this connection, so the same connection, here you have the column and this is the beam, and this beam and column is connected through a bracket, and this bracket is welded to the beam, and then we have this joint and these bolts. So if you do the finite element analysis, you see this yellow region that is a higher stress in this case, and that is a tensile region, and this side you have basically compressive forces. So due to this moment, there is load is coming here, so due to this moment there is a tensile force that is generated on the top side of the bolt, and a compressive force is generated in the bottom part of this connection. So in summary, we can say that these bolts are subjected to direct shear as well as a tension due to the moment. Now the question is how we find these tensile forces in each bolt. Does these forces are same, or it will depend upon some kind of distance from the neutral axis. That is the previous video, same thing we have illustrated in case of shear force, and then in that part we say the forces is proportional to the distance. Can we do the similar exercise in this case also? So let's see. So here I have made the same beam and column connection. So this is the part of beam and this is column, and these are connected through bolts. So this represents bolt, and there is a load P that is coming on this beam, and this is a distance or eccentricity of E from the basically column to this load. Now these bolts, so this is from bottom end of this beam to the first bolt center, this distance is given, this distance is equals to H. So if I apply this force P, what will happen? These bolt will experience a shear force. So here also a shear force will come and shear force will come. Apart from this will try to rotate. So this force will try to rotate this beam, and if I do that, it will look something like this. So this is an exaggerated picture, but you can think in terms of concepts. It can help you to understand. So what is happening in this case? This beam will try to rotate, and once this beam tries to rotate, these bolts will be pulled. So there is an elongation in this bolt. Similar, but all bolts will have not similar elongation. Some will have more, that is the farthest bolt, and some will have less. And even there is a point, this point somewhere here will have no elongation. So we will call this point as a neutral point. So there is a no elongation at this point, and this side of the bolt or this side of the plate or connection, you see there is basically a compressive force. So this is trying to push this column in this direction. So there is a direct contact in this region of the beam bracket, that is the bracket connected to the beam and the column. So there is a direct connection, and this is trying to push in this region, this is trying to push this plate. So there is a basically direct contact in this case. Now how to find the location of this neutral axis, that is neutral point, is basically complicated process. Many process and many method involves, and in the literature some of them says you can do hit and trial method. For simplicity we will assume, or literature has assumed, that this point lies at a distance of h by 7 from the bottom of this beam plate, so or beam member. So you see in this case I can say this point is a distance of h by 7. So this is my neutral axis. So bolts above this will have tension, and this will have more tension because this is a elongation is more in this case, this beam. So I can say something like this, and then here the next bolt will have this much of elongation, so this much of tension, and this bolt will have, now this side we will have basically compression zone. So the whole plate in the bottom side, so this whole plate basically will be in compression. So there is not only the bolt, basically bolt will not win that much compression, the plate will win the compression. So this is important point. Here we will have plate is in compression. So the magnitude of moment that is coming on this plate is equals to force times distance, that is P times E. Force is P and eccentricity is E. Now how to find this tensile forces as well as direct shear forces, and how we can find the resultant force. So my task is, what is the resultant force in each bolt? So if you remember, in the previous video we says this is under the linear elastic zone, so we can use superposition principle, and the same assumption we are also making here, that is to find the total force in the bolt we will use superposition, that is two component. First we will calculate force due to P, in this case this is shear, and we will calculate the tension due to moment M, and then we will sum these two forces. So if due to the shear force is F1 and due to tension force is F2, then we have to basically sum these forces, and we have to also sum these in terms of vector, because these two forces are not in the same direction. We will see this. In fact, these two forces are perpendicular to each other. If you remember, earlier I have shown you one bolt and tensile force in this direction, and this is the shear force. So I can say F1 in this direction and F2 in this direction. So these two forces are perpendicular to each other. So let's first find our forces due to direct shear, that is due to P. So if you look at this column from the beam side, it will look something like this. So you have bolts and the total force on coming is P. So each will have some amount of force. So this is on the hole. So this force is on the hole. Similar force will come in the downward direction on each bolt. So I am showing here only few bolts. You can similarly show other bolts. Now if I consider the equilibrium, so this force F1 I can say on each bolt is basically P divided by N. So because there are N number of bolts, so we can say F1 is equals to P divided by N, where N is the number of bolts that we have in this case. Now let us find tensile force due to moment M. So as I said earlier, this force will something like this. On the top it will have higher magnitude of tension, and slowly it will reduce, and a point will come where you have no elongation, that is a point of neutral axis, and after this whole plate is in compression, under compression. So we can say basically these compressive forces are along this direction. So now we have to find the tensile force due to moment M. So in this case moment is M, that is equals to P times E. Now to calculate this or to determine the tensile force, we will make one assumption, and assumption is tensile force is proportional to the distance. What this means, that if I have a bolt Ti, that is the tension inside the bolt ith bolt. So here I have, let's say this is my ith bolt. So I can say tension in the ith bolt is proportional to the distance of this bolt from the neutral axis, that is Ti is proportional to by I. In other words, if I put a proportionality constant, I can write Ti is equals to K times by I. In other words, we can say, let's say this is bolt number 1, this is 2, this is ith, and this is nth. So we can say T1 is nothing but this is equals to, so this is equals to K times by 1. Similarly, I can write T2 is equals to K times by 2, Ti is equals to K times by I, and Tn is equals to K times by N. So now question is how we can find this constant K. So basically K is a constant and we have to find its value. So this is very similar to previous video. In that case we have considered equilibrium. So this K can be found by considering equilibrium. So we will consider equilibrium of forces and we will consider equilibrium of moment. So if I consider moment, we can write total external moment, that is P times E. External moment is equals to total internal moment. So this external moment is P times E, also called M, and the total internal moment will be having two components. One is due to tension and another component that we will have, that is due to compression. So we will try to find these two separately. So let us first find moment due to tension. So total moment due to tensile force, or we can say tensile moment. So total tensile moment will be, so you have these bolts are here. So this bolt and this one. So this is Ti and this distance is basically by I. And this is first bolt, let's say. So this is y1 and the corresponding force is T1. So we can say T1 times y1 plus T2 times by 2, and this goes to Tn times by n. If you remember, we have written, in general I can write basically this is summation. So I can write this is simply sum of Ti by I. I goes from 1 to n. If you remember what was the value of Ti, so that is k times by I, and this multiply by I. K is a constant, I can take this outside. So this is summation of by I square. So let's call this moment as m dash. So m dash is the moment due to the tension. So m dash is moment due to tensile force. So this is unknown. For the time being, this is an unknown quantity. So in terms of m1, m dash, we can write k is equals to m dash divided by summation by I square. We can also write tension in ith bolt in terms of m dash. So tension in ith bolt is k times by I, and now I know value of k, so I can write this is m dash summation by I square, and this multiplied by I. So in summary, we can write Ti is equals to m dash by I divided by summation of by I square. So what was my target? My target was to find k. But in finding k, we have introduced another term, that is m dash, that is another constant. So basically now we have to look for m dash, how we can find m dash. So first we will consider the force equilibrium. So let us consider force equilibrium. So that is total tensile force T is equals to total compressive force C. So I can write C is equals to total tensile force will be T1 plus T2 plus Ti, and this goes up to Tn. So Ti is given by this formula. So T1 will be m. So this formula is here. So T1 will be m times by 1 divided by summation by 1 whole square. Basically by I whole square. This is nothing but summation of by I whole square, that is nothing but by 1 square plus by 2 square. So this is by 1 square by 2 square, and this is up to by n square. So this goes up to by n square. Now similarly I can write Tn, that is m by n divided by 1 square by 2 square, and this goes up to by n square. So if I take LCM, that is by 1 square plus by 2 square, and this is by n square. So this is m times by 1 plus by 2, and this goes up to by n. In short, I can write the compressive force is equals to m times summation by I divided by summation by I square. So this is my compressive force, which is equals to the sum of the tensile forces in all the bolts. In this case, this is m dash. So I have to put this m dash. So these are m dash. Now we will consider the moment equilibrium. So total external moment So let us write here moment equilibrium. So total external moment is P times E, and then I have to equate this with total internal moment, that is moment coming due to the compressive force in the bolts or in the plates plus total moment due to the tensile force. So moment due to tensile force, so let's call moment due to tensile force plus moment due to compressive force. So this is equals to PE is equals to moment due to tensile force. We already know that moment due to tensile force is M dash. So remember, what is my target? My target is to calculate M dash, that is unknown, plus moment due to compressive force. Now this is tricky part. Now if you see, this is my neutral axis, and up to this point this is in tension and this part is in compression. So this zone is under compression and this distance is h by 7, and we calculated total compressive force is equals to C, and that value is nothing but M dash summation of by I divided by summation of by I square. So this value we have already calculated. Now to calculate the moment due to this compressive force, we can assume this is located at the centroid of this part. So this triangle. So this triangle centroid will lie at a distance of 2/3 from the top, that is this distance is equals to 2/3 of h by 7. So moment due to the compressive force will be C times 2/3 of h by 7. Now if I plug this value here, so I can write PE is equals to M dash plus C is nothing but M dash summation of by I divided by summation of by I square times 2/3, that is 2 by 21 times H. So we can write PE is equals to, if I take M dash common, so this becomes 1 plus 2 by 21 and H is here summation of by I divided by summation of by I square. So now I can get value of M dash. So M dash is nothing but PE divided by this term, that is 1 by 1 plus 2H by 21 summation of by I divided by summation of by I square. So now once I know M dash, I can calculate tensile forces in any bolt. So if you remember, earlier we derived expression for tensile forces Ti in terms of M dash. So that is Ti is equals to M dash times by I divided by summation of by I square. So now if I plug this value of M dash, that is PE divided by 1 plus 2H by 21 summation by I divided by summation by I square, and this multiplied by this value here by I divided by summation of by I square. So this will give me the tension in any of the ith bolt. So now we have calculated total force in this bolt, one due to tension, another due to shear. So if you remember, let's say this is your bolt, this force, that is the tensile force Ti, is given by this expression, and this expression, this force, that is the shear force, that is basically given by P by N. So this was earlier I called one is F1 and one other is F2. So we calculated the tensile forces as well as shear forces. If you want to calculate the total force, you have to square and take the root. But code does not say you to calculate the resultant force. Code gives different formula to check whether this kind of bolt is safe or not. That we will discuss under design of this bolt. So let us discuss how we can design such kind of bolt that is under shear as well as under tension. So in the first step, we will assume some diameter of the bolt, pitch diameter, pitch distance, edge distance, and then we will calculate a strength of the bolt. How we calculate a strength of the bolt, that we have earlier discussed in some of the videos. Now in the next step, we calculate how many bolts are required for given moment M, and M is nothing but P times E in this case. So we can calculate an initial guess for the total number of bolts using this expression. And what are these terms? We have earlier discussed this. In this case, one important point, N dash is number of vertical rows of bolt. For example, in this case, there are 2 vertical rows of bolt. So this N dash is equals to 2. P is the pitch distance and VSD is the design shear force that we can calculate using IS 800. Now in the third step, we have to calculate shear force in the extreme bolt, that is the largest bolt from the neutral axis, because it will be the critical bolt. So we have to calculate the shear force VV for the farthest bolt, and calculate the tensile forces also for that bolt. Of course, in this case, tensile force will be maximum. VB will be same for all the bolts. Either you take the extreme bolt or you take any other bolt. In all cases, the VB value will be P by N, but TB value depends upon distance by I. So if you take the farthest bolt, TB value will be maximum. And once you know TV and VB, code gives a formula to check whether your design bolt is safe or not. So check the safety of bolt according to this formula. So this formula says some shear component and some tension component, and this has to be less than equal to 1. Now in this formula, VSV is the factored shear force acting on the bolt that we are calculating, and this is the design shear capacity. So this design shear capacity can be calculated using this clause, and this TDB, that is design tension capacity, that can be calculated from this clause, and these two parts, that is VSB and TB, that is the factored tensile force and factored shear force, is different for different problem, and you have to calculate your own using doing some analysis of the structure. So how we calculate this 10.3.2 and 10.3.5, that is the shear capacity and tensile capacity. So this is given in clause 10.3.2. So you can use this formula to calculate VDSV, and similarly you can use clause 10.3.5 to calculate this shear capacity, basically tension capacity in this case, which is minimum of this one and this one. So this we have already discussed in previous video. So we can basically summarize whatever we said in the today's lecture. So we said if you have a bolt that is in tension as well as in shear, in that case you have to find tensile force and as well as the shear force, and then you have to basically use some kind of codal provision to check whether my bolt is safe or not. To calculate the tensile force, you have to make assumption that is the bolt distance from the neutral axis is important for calculation of the tensile force. In other words, tensile force is proportional to the distance from the neutral axis. So we can stop here. Thank you.